Okay, hello again. We're going to talk about, continue with chapter 5, and we are going to talk about chapter 5 let's say section 5.3. Okay, graphing polynomials. So let's get started. So here is, so before I do problems, I want to talk about what graphing polynomials is all about. So let's do an example and then we go back and do some problems. I hope you're doing well. So what we like to do is we like to graph a polynomial. Now, how do we graph a polynomial? So let's look at an example. Now, we know that polynomials are given in two different forms. We can write them in this form, right? Or we can write them in this form, which is the factored form. So every polynomial can be factored into a sub n and then bunch of factors. And these factors are linear factors. That means x in the factor is to the first power, right? So we got bunch of factors. How many? As many as we have the degrees. So if the degree is 3, then we have 3 factors. If it's 5, we have 5 factors. Okay, so how do we graph something like that? Let's see. Let's say we have 2 and then we have x minus 1, maybe x plus 2, and then x minus maybe 4, right? So to graph this, what we need is, first of all, we need AND behavior. Now we talked about AND behavior. Then we need the y-intercept and x-intercept. Right? So we need the intercepts. Now, it could be more than one x-intercept, but there is only one y-intercept. And then what we need is the behavior at the x-intercepts. How does the graph behave at those points? So first we need AND behavior. AND behavior has to do with leading term. So the leading term for this polynomial, as we know, is the product of the leading terms of every factor. So 2 is just by itself, so we're just going to have to write 2. That's the leading term by itself. Here the leading term is x, here is x, and here is x. So it's x times x times x. And that is 2x to the third power. Now 2x to the third power, it determines the AND behavior. So what is the AND behavior? Well, on the right, when x goes to infinity, positive, this goes to 2 infinity to the third, which is just infinity. So that means the behavior looks like that. And on the left, when x goes to negative infinity, this goes to 2 negative infinity to the third. And the negative to the third is negative, and this is a positive number. So positive times the negative is negative. That means on the left it behaves like this. So to graph it, all we have to do is graph the coordinate plane. And now what we need is x and a y-intercept. Now the y-intercept is very easy to find. All we have to do is substitute what? 0 for x, right? So 2 times 0 minus 1 times 0 plus 2 times 0 minus 4, right? So that's negative 1, negative 2, positive 8 times 2 is 16, right? So let's put it over here, 16. All right, now we need the x-intercepts. Now, that's a good thing about being in factored form. X-intercepts are these numbers, right? These numbers, but since you have to set this equal to 0 to find the x-intercept, that means the x-intercepts are opposite of those numbers, right? Opposite of those numbers. So if you said x minus 1 equals to 0, right, to find the x-intercept, you have to set the whole thing equal to 0, right? That means this equals to 0, this equals to 0, or this equals to 0. So if you set this equals to 0, then x equals to 1. So 1, 0 is one x-intercept, and the other one is negative 2, 0. Negative 2, 0. And the other one is 4, 0. 4, 0. Okay? So 1, 4, which is 2, 3, 4, and negative 2, which is that right there. Okay? So, and we know the end behavior looks like this, right? So this comes over here. Now we have to decide how does it behave at this point, right? So to do that, we're going to come back here. Let's talk about it here, and then we come back and finish the graph. So if the polynomial has this factor with some power, right? If that power is even, if n is even, then we get something like x minus c to the second power, or maybe x minus c to the fourth power, and so forth, right? So if it's to the second power, then the graph at c, because opposite of negative c is c, so c is the x-intercept. Now, the way it behaves is that it doesn't cross at this point, it bounces back like that. If it comes from the bottom, it also bounces back down, okay? Now, if it's 4 or more, then not only it bounces, it also flattens a little bit. Flattens, I mean, it does that. So before it touches here, it gets close to the axis and then touches that and stays close and then bounces back out. So that's how it behaves if it's 4 or more. So bounces and flattens. Now, if n is odd, then what happens is this. So n is either 1, or it could be 3 or more, right? Now, if it's 1, it just crosses. That's it. Just crosses at that point, okay? So crosses at that point. If it's 3 or more, then again, it crosses and flattens. So it gets close here before it bounces off that way, and it's close here before it bounces off. So it flattens and crosses. Okay? So that's how it behaves at x-intercept. So let's go back here, and you see that here the x-intercept is negative 2, which is this one. Now all of these are to the first power, so that means at these points we just have crossing, right? Crosses, and then has to go here, and it crosses, it has to go here, and then it crosses, has to go there. Okay? So that's the best we can do, and I just erased what I graphed, but I can do it again. So that's the best we can do with algebra. There. Okay? That's the best we can do with algebra. Now, if we want to graph this exactly or precisely, much more precisely, we're going to use calculus. So what I'm going to do, I'm going to graph it with a technology here. So I'm going to graph this y equals to 2, and we've got 3 of these. So I'm going to move it to put x minus 1 there, and then put x plus 2 there, and put x minus 4 there. So as you see, that's the graph that is graphed in a much more precise manner. So let's see. So does it look like what we graphed here? Well, let's see. Yeah, kind of. For example, we can't really tell with algebra where that top of the hill or the relative max is. See, I put it somewhere else, but here is not, of course. So what I did, I put it over here, but as you see in the graph, is actually over here and then crosses, right? We can't really tell exactly where that point is with algebra. And also the min here, this is right at negative 20 something. Mine, I don't know where it is. Maybe it's like 3 or so, right? So, but that's the best we can do with algebra, with college algebra. And that's good. That's a good graph. Okay, now that we know how to graph these, let's do some of these problems. So we want to do maybe number 6 and number, so I'm going to do number, let's see, number 6 and 7 is good. So to graph this, let's quickly do it together. So what do we need to graph this? Well, let's see what we need to graph this. Let me get my microphone in the right place. There you go. All right. So what do we need to graph this? Well, we talked about it. What we need is, let me get a red pen here. So what we need is the n behavior, right? All right. So what's the n behavior of this? Well, what's the leading term? So leading term would be 2 times t times t times t, right? So that's 2t to the 3rd power. And that is, of course, we just did that, right? So on the right, when t is infinity, that would be infinity. And on the left, when t is negative infinity to the 3rd is negative infinity. So when x is negative infinity, y is negative infinity, so the points go this way, right? So that's the n behavior. Now, what is the y-intercept? Well, the y-intercept is c of 0, which is 2 times 0 minus 4 times 0 plus 1 times 0 minus 6. So negative times the negative is positive. 2 times 4 is 8. 8 times 1 is 8. 8 times 6 is 48. Right? So that's it. Now what about x-intercepts? Now, as we discussed before, x-intercepts are the opposites of these numbers. So if you set this equal to 0, then this equals to 0, this equals to 0, and this equals to 0. So opposite of negative 4 is 4 and 0, so that's 1 x-intercept. Opposite of 1 is negative 1, 0 is another x-intercept. and opposite of -6 is 6 and 0. Okay, so the graph of this will look like, let's see. So where is the y-intercept? 48. Let's assume this is 48. Okay, and 4 is 1, 2, 3, 4 right here, and also 6 and -1, right? And remember, n behavior looks like this, right? So, and n behavior at x-intercepts, right? Since all of them are to the first power, they all just cross at the x-intercept, right? They just cross. So here we have a crossing here. Here we also have crossing, and here we also have crossing. So we come over here, it crosses, right? Goes over there again. We don't know exactly where, but we know it goes over there. Comes over here and goes over there, and then, right? That's the best we can do with what we have with algebra. Okay, so let's do another one. Well, number 7 is the same, right? So let's get the n behavior. Would be 3 times t again, times t, times t, right? And that's 3t to the third power. And again, n behavior would be the same as before, right? All right, what about the y-intercept? Well, the y-intercept would be c of 0 again, c of 0. And c of 0 is, what is it? Well, is 3 and then 0 plus 2 and 0 minus 3 and 0 plus 5. So that is basically 3 times 2 times -3 times 5, which is a negative number. And this is 6 times 5 is 30 times 3 is 90. So it's -90. And now, what about x-intercepts? X-intercepts are opposites of these numbers, right? So it's -2, 0, 3, 0, and -5, 0, right? So we can easily graph it. Let's graph it. Again, what do we have? We have the y-intercept, which is -90. Well, let's assume this is -90, right? And the is not drawn to scale, of course. So -2 is one x-intercept, -5, 1, 2, 3, 4, 5 is another x-intercept, and 1, 2, 3 is another x-intercept. Okay, so we know the n behavior looks like this. And the crossing, again, they're all to the first power, right? So all the crossings are just crossing, no bouncing, no flattening, right? So we come over here and then go over here and then go over there and go over here. Again, we don't know exactly where this top is, whether this comes down here and goes back up here, maybe. But that's the best we can do with college algebra. Okay, so that's that. Let's do one more. Let's do number 10. So here we just have to find the x-intercepts, but what I like to do is I want to actually I want to actually graph it. So let's do that. So we want to graph it we have enough room. Okay, so what we have to do is we have to write this in factored form, because remember, we don't know how to graph this if it's not in factored form, right? And to do that, we're going to talk more about factoring these things, but for now, what can we do is we can factor the we can factor the 2 out of the numbers and t squared out of the t's, right? And then what do we get? If we take that out of 2t squared out of here, you get t squared. And if you take it out of here, you get negative 4t, right? We just have to divide. And out of here, we get just 3, right? All right, now we can factor even more. So we have 2t squared, and then we have what? We have 2 factors, and I think everybody knows how to factor that. We need 2 numbers, you multiply, you get positive 3, and you add, you get negative 4. So that is in factored form. Now we're going to assume that this looks like, instead of t, I write t minus 0 squared, right? That's the same thing. But this way we can tell that the 0 of this is 0, right? The x-intercept is 0. And then for this one, x-intercept is 1 to the first power. And x-intercept here is 3, again to the first power. So what's the leading term? Well, we don't have to really figure it out because we already know leading term, right? So leading term is 2t squared, 2 to the 4th power. So now, what does it look like on the right? Well, if you put infinity here, you just get infinity, right? Positive. Even if you put negative infinity on the left, negative to the 4th is positive, you still get positive infinity. So that's the end behavior. Goes to the positive infinity this way and that way. Okay, and the y-intercept is easy to find in the original form, right? Because they all have t's. If you put 0 here, you just get 0. So 0, 0 is the y-intercept. And the x-intercepts, of course, are what? Well, we go over here. 0, opposite of that is 1, opposite of that is 3. So this is x-intercept, this is x-intercept, and this is x-intercept, right? So let's graph it. So x-intercept is 0, 0, and the y-intercept is also 0, 0, so it's the same place. And then 1, 0, and then we have 3, 0, right? That's a 3. That's 2 and that's 3. And we know that this behaves like this, right? All right, now how does it behave at 0? Let's go look at it. So 0 is in this factor, and this factor is to the 2nd power, so it has to bounce. So at 0, it bounces. Now we know it doesn't bounce from the bottom because it's up here, right? It has to bounce from the top. So it comes over here, it bounces off this point. Now what's going on at 1? Is this just crossing? So it just crosses at 1, right? And what's going on at 3? It just crosses, right? So it's going to look like something like that. Now, the exact graph, we need what? We need a more better tool to deal with it, more powerful tool. So this graph is going to look like, let's see. Instead of t, I can use x, or I can use t, doesn't matter, but I think x is better. I just use x minus 8x to the 3rd power and plus 6x to the 2nd power There. Okay. So does it look like something we graph? Well, I think so, right? Let's see. Does it look like that? Kind of, yes. Makes sense. You see, it comes here, it bounces, goes up there, and then how much does it come down here? We don't know exactly. How much does it go up here? We don't know exactly. Now, with algebra, we can graph more points and figure out where which direction it goes. But that would be tons of points we have to graph, right? With calculus, we kind of can tell this shape easily. All right, so that was another one. So let's do we did number 10 already. Okay, let's do another one. This one. So now, number 24 is about intermediate value theorem. So it says for the following, use the intermediate value theorem to confirm that the given polynomial has at least one zero within the given interval. Now, what do they mean by that? So let me grab this number. I'm going to do number 24. Grab this whole thing and then talk about it. So, what do we mean by intermediate value theorem? Well, what we mean is this. If we have a continuous function, let's say we have a continuous function, right? And so let's call that, so polynomials are continuous functions, right? Continuous means they have no breaks in them. So if we have a point here, let's say A, and then I have point here B. So at B here, let me extend this a little bit so I can. So at B here, the y value obviously is positive. That means P of x is what is positive. So this number right here is a positive number, right? This number right there. Okay, so we can say that P of x is positive at what? At B. And P of x at A, that means P of A is negative, obviously. Because if you come down here, the y value here is what? This is a negative number. Now, we say that the intermediate value theorem says that since P of B is positive and P of A is negative, then this graph must have a zero. That means must have an x-intercept, real zero, between A and what? And B. Now, if the zero is real, of course, it would be what? It has to be on the x-axis, right? So between A and B, it has to have a zero. Now, if the zero is real, it would be on the x-axis. So now it has no choice but cross the x-axis because it's below the x-axis at A and then above the x-axis at B. So it has no choice but cross. Now, does it have to cross only once? No. You can think of a situation where we have A and B. So the graph is negative here, and then it's going to go up maybe several times, up and down, before what? Before it goes there. So in this case, we have more than one. We have many numbers between A and B where the function is zero, right? So that's the idea of intermediate value theorem. So here we are given a function, f of x is x to the third minus 9x, right? Now the question is, what is f of negative 4 and what is f of negative 2, right? If you don't want to do the arithmetic by hand, you can use a calculator to do the arithmetic. Now I don't want to graph with the calculator. I just want to do the arithmetic with the calculator. So what I do, I go to y equals 2, and I put that function in y1. So that is what? That is x to the third power minus 9x. And I go to the table set. Make sure the independent is on ask so I can put numbers in there. So if you see it like that, make sure you go over ask and press enter to change it. And then you go to table. Then delete if you see any numbers there, just delete them. And then put negative 4. So for negative 4, that's a negative what? Is a negative 28, which is of course negative. And what about negative 2? That is 10, which is what? Positive. So if this is negative 28 and this is 10, then this function at negative 28, I mean not negative 28, what am I doing? Sorry about that. Negative 4, and this is negative 2. So at negative 4, this is negative 28, which is negative. And at negative 2 is 10, which is positive. So the graph is here, and then it wants to get there. How? Well, it has to cross the x-axis. So there must be, at least, right? At least a 0 in interval what? Negative 4 to negative 2. There has to be at least one. That's what this theorem guarantees, that there has to be at least one. Okay? All right. So let's do a few more. Let's do number 3. So, and we also want to graph these. So I'm going to not only talk about multiplicity, also. I know we talked about, let's do some scratch work up there. We have a space. So we know polynomials can be given in these two forms, right? A sub n x to n plus 0 dot 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 a sub 0, or in factored form, right? A sub n x minus c1 and then x minus c2 dot 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 x minus cn. Now, of course, some of these c's could be the same, right? And we know that an nth degree polynomial has n zeros or roots, n roots or zeros, right? So that's a theorem that we accept, that if we have a polynomial that is like 4th degree, then it has to have 4 roots. Now, the roots of polynomials could be rational roots. So what do I mean by rational? Examples is like, for example, a polynomial x squared minus, let's say, 4 over 9, right? Now, what are the roots of this? If you set it equal to 0, the roots would be x squared equals to 4 over 9. So x is plus and minus square root of this is 2 over 3. So this is a rational roots. This is a rational root. So another example would be p of x equals to x squared minus 1. If you set it equal to 0, x squared equals to 1 is plus and minus 1, right? So these are rational roots. Now polynomials can also have what? Polynomials can have irrational roots. So irrational roots. How can we have irrational roots? Well, let's say we have a polynomial that is x squared minus 2. Well, if you set it equal to 0, then x squared equals to 2. Then x is what? Plus and minus the square root of 2. That's an irrational root, right? These are irrational. Or it could be complex imaginary. Complex imaginary. Imaginary. So what's an example of that? Well, maybe x squared plus 1. If you set it equal to 0, what do we get? We get x squared equals to negative 1. So x is what? Plus and minus the square root of negative 1, which we know is just I, right? That's a complex imaginary. In fact, it's pure imaginary in this case, right? So there are 3 different types of roots you can get here. So these c's could be any of those numbers. And could also be the same. For example, can we have roots that are the same exactly? Yes. What if we have a polynomial that looks like this? X minus 1 to the 3rd power. And then times what? X plus 2. Now this polynomial has, obviously, if you set it equal to 0 here, what do we get? Well, we get x minus 1 to the 3rd equal to 0. That means x minus 1 is 0. So x is 1. And here we have x plus 2 equals to 0. So x is what? Negative 2. Now, we just said here that degree polynomial has to have what? N roots. What degree is this? This is 4th degree. If you find the leading term, that would be x to the 4th. But we only see 2 roots here. How does that work? Well, let's put them right here. So these are the roots which we found, which is 1, negative 2, and 1, right? So there is something called multiplicity. Well, terrible handwriting, but multiplicity. So negative 2 here counts only once. Why? Because the power that the root comes from has a power of 1. So the power of the factor that the root comes from is 1. And the power of the factor that this root comes from is 3. So the multiplicity of that root is 3. You can think of this as this root counts 3 times and this root counts only once. Because if you write this in expanded form, what are you going to have? You're going to have x minus 1 times x minus 1 times x minus 1. So it counts 3 times. So the total number of roots would be the sum of the multiplicities. So 3 plus 1 is 4, and it has 4 roots. So that's the idea of multiplicity and different types of roots of polynomials. So what roots and what multiplicities does this have? Well, we can easily see this is roots and this is multiplicity. So what is the root here is the opposite of this number, negative 2. What's the root here? 3. Now notice this is the 5th degree polynomial. So negative 2 counts how many times? 3 times. And 3 counts 2 times. So total is 5. We have 5 roots, right? And those are the 5 roots. Negative 2, negative 2, negative 2, 3, 3. Those are the 5 roots. Okay, that's the idea of multiplicity. And here is another one. Oh, we forgot to graph it, but Well, we graph this one. We can graph this one, but the numbers are big, but that's okay. Here we go. To have enough room to graph it. So let's move on. So multiplicity, I just do it here. It's very easy to think of and figure out. Now, what is the root for x squared? Is 0, right? So we have a root of 0, and the multiplicity is 2. And what is the root for this? Well, the root for this is what? We have to set it equal to 0. So the root would be negative 3 over 2, right? Negative 3 over 2. And what's its multiplicity is 5. And the root here is 4. So and multiplicity is what? Is 2. Right? Okay, so now we can easily graph this. So what do we need? We need the end behavior. The end behavior is given by, so the end behavior is given by what? By x squared times 2x to the 5th power. So it would be 2 to the 5th power. Let's do some scratch work here. So 2 to the 5th power is what? 2 times 2 times 2 times 2 times 2 is 32, right? And then x to the 5th power. So that would be 32 x to the 5th power. And then this one would be x to the 2nd power. So the leading term is 32 x to 2 plus 5. 7 plus 2 is 9. So this is a 9th degree polynomial, right? So again, since this is odd here, let's find out the end behavior quickly. If x is infinity, infinity to the 9th is infinity. If x is negative infinity to the 9 is negative infinity. And since this number is positive, positive times negative is negative. So that's the end behavior. Now what about the y-intercept? Well, the y-intercept is if we put 0 here, 0 here, 0 here, everything is 0. So it would be 0, 0, right? Because that 0, that x makes everything 0. And the x-intercepts we already have. X-intercepts are 0, right? 0. We have negative 3/2, 0. And then we have 4 and 0, right? Now, also the behaviors at 0, the behavior is what? Is either bouncing this way or that way. We don't know. We're going to figure out. At negative 3/2, right? So that's 0. At negative 3/2, what's going on? Well, negative 3/2 is to the 5th power. So here is going to flatten and then cross. And at 4, what's going on? At 4 is also what? Is bouncing, either this way or that way. So let's graph this. So I want to graph it. Now the y-intercept is 0, that's that. And then we also got a 0 at 0, so it's the same point. So x and y both are 0 here. And then negative 3/2 is right here. Let's say negative 3/2 is here. And 4 is over here somewhere, right? And the end behavior looks like this, right? So what's going on at negative 3/2? So it's going to come over here, really flatten, get close here, get close, and then cross, and then come out, right? And then it has to come back and cross here. At 0, does it cross? Let's see. No, it bounces back up. It bounces back up, right? Let me see. Oops, oops. Oh, I erased everything. Sorry about that. Okay, so come over here, and then it goes over here, and it crosses, and over here, let's make sure we got everything correct here. That's to the 5th power at -3/2, that's correct. This one at 4 it bounces. Okay, so it bounces over here at 0, right? So 0 right here, it bounces because it's 2. Now it comes over here, what can you do at 4? Well, at 4 it bounces back up like that. Now I give you is not a pretty picture, but it's correct. So let's look at the actual picture and see if we get something close to that. There we go. Y equals to x squared, and then we got 2 of these. Let's see, I don't know if you see it down there, but I'm actually typing 2x plus 3, and then I have to raise it to the 5th power, and then inside the other parentheses I have x minus 4, and I have to raise it to the 2nd power. There. So let's see. It looks like we kind of have it's a little bit, their values are so big that we have to zoom out to kind of see them. Let me zoom out even more. You can get a picture of it. That value is really high, so I'm going to bring it down like this. See if we can get that. That is a really big number. Alright, so here you go. We got it. So you see with the college algebra we can't exactly tell. But here you go. Look at that. Not bad. Now, this bump right there, the bump that we have right here, right? The bump that we have right here, let me get back. This bump kind of disappeared. You know why? Because these numbers are so big. Look at that. This little bump here, it disappeared. And it comes over here. So there is a bump there. You can see it if you zoom in. And then it comes back up and then bounces back up, right? So that's not a bad picture based on, you know, college algebra. It's like you only have a screw and you want to overhaul a carburetor, right? So not bad. I think we did a good job. All right. So 36. What's 36? And so in 36 we can talk about here. We just have to find the zeros and multiplicity. I have to write this in what? In factored form to find the zeros. So we have f of x. X is good, so that's a good factor. So this is a quadratic, so we need 2 factors. So what we have to do is, since the coefficient is 4, we have 4, and then we have to have 2 linear factors. And for this one, coefficient is 1, so I'm not going to write it, and we need 2 factors. So all of these are basically x minus, x minus, x minus, x minus, right? So to find these two, we use quadratic formula for this. So let's use quadratic formula. X equals to negative b, which is 12, plus and minus b squared, which is 144, minus 4ac. Now what is a? 4, and what is c? 9, and then over 2a. What is a? 4. Now inside here would be 4 times 4 is 16 times 9 is actually 144, so that's 0. Inside the radical is 0, so that's just 12 over what? Over 8, which is 3 over 2, right? So now, since this is a quadratic and inside here is 0, so that is a repeated root. So we have 2 roots, that is 3 halves. So we have to put 3 halves here and 3 halves here, right? Now what about this one? We do another quadratic, and b is negative 8 plus and minus the square root of 8 squared is 64 minus 4 times 1 times 16, right? And then over what? Over 2a. Now inside here again is 0, so we're going to get what? We're going to get negative 8 over 2, which is negative 4, right? So that would be x minus negative 4, x minus negative 4. Again, is a repeated root, right? So those are the factors. So they're what? The roots are 0 for x. And then we got, if you write this way, put the 4 before x. So it would be 4x. And then x minus 3 halves to the second power, right? Let me erase that, we don't need it anymore. And then we have x minus negative 4 is actually x plus 4 squared. So we got 0, we got negative 3 halves, and we have what? Negative 4. And what are the multiplicities? Well, for 0 is 1, for this one is 2, and for this one is 2. So this is a 5th degree polynomial and has how many roots? Has 5 roots. And again, just like we graphed the one before this, we can graph this easily. You can practice and graph this. And this program that I'm using is called Algebra. And if you go to, let's say, search for Algebra, you see, it has to be .org, right? Nothing .com. And then you can download the platform that you like and use it. I use the Windows version of it. Okay. All right, so let's do a few more of these. Let's do number 40. So we need to graph these. Well, we graphed a bunch of these already, but I'm going to do one more here. Let's do this one as well. Again, here, this would be x to the second times what? Times x. That's the leading term. So the leading term is x to the third power, right? What's the end behavior? Well, since you know the leading term is x to the third power, the end behavior would be, if you put infinity to the third, would be infinity. Put negative infinity to the third would be negative infinity. So that's how it behaves. What is the y-intercept? If we put a 0 here and put a 0 here, right? That would be 3 squared, which is 9. This would be negative 2 squared, which is 4, and 4 times 4 is 36. So 0, 36 is the y-intercept. And the x-intercepts are, well, negative 3 twice, right? So it's negative 3. And the other one is 2. Now, how do they behave at these points? At negative 3 and 2? Well, at negative 3, it bounces whether from the top or from the bottom, depending on where it is, right? And then 2, since the power is 1 here, just crosses, whether this way or the other way, doesn't matter. Okay, so here you go. So the graph of this will look like, so where is negative 3? 1, 2, 3. And where is 2? That's 2. And the y-intercept 36, let's assume that's 36. And the end behavior is this way. So it comes to negative 3, it has to, just a moment. Let's see. Negative 3 has to, oh, my fault here. When I did the y-intercept, that's a arithmetic mistake. There you go. When we did the y-intercept, that's 9 and that's negative 2, not 4. So that's negative 18. There. How did we find out we made a mistake? Well, I made a mistake. You're not here to say anything. So usually in a face-to-face class, I say we because nobody says anything. So it's your mistake too. But here is mine. I take it. So we come over here. So we have to bounce at this point, right? And we have no choice but cross the y-intercept. Now at 2, what's going on? Since this is to the first power, it just crosses. There. That's the best we can do with college algebra. Okay? Again, the problem here was that the y-intercept, and I got 36 since I thought that was 2, but it's a 1. Everything else is the same as before. So we got that under control. Let's do number 40. Again, you want to do one more? We could quickly. Or there. Okay, so what is the end behavior? Well, this is x to the third, right? And that's x to the second. You see, you should write notes clearly. Don't do it like me. You see, if you do it like that, you may make a mistake, right? And I did. So x to the fifth, right? So that's the end behavior based on that. So the end behavior would be, if I put infinity in here, I get infinity, positive. If I put negative infinity, I get negative infinity. So it looks like that. Now what is that's the end behavior. Now what is the y-intercept? Well, the y-intercept is, if I put a 0 here, right, put a 0 here, this would be negative 1 to the third, which is negative 1. And this would be 3 to the third, which is 9. So negative 1 times 9 is negative 9. And the x-intercepts are, well, 1 and what? And negative 3. Right? Now, what's going on at negative 3? Negative 3 to the second, either, since it is to the second power, either bounces from the top or from the bottom, depending on where it is, right? And at 1, since this is 3, it gets close here and crosses and comes back and gets out and then it stays close, kind of like that. Not with that much exaggeration, but it flattens a little bit. Okay, so that's 1. So graphing it, now it's easy. The y-intercept is negative 9. X-intercepts are negative 3 and 1. And the end behavior is this way. So at negative 3, it's supposed to come over here, stay close, right? And then Did we make another mistake here? No, that's negative 18. So at negative 3 it has to as negative 3 it has to bounce. I mean, I was crossing it. So just a moment. I thought that was 3. So it bounces back down, right? And it has to go through what? The y-intercept. What's going on at 1? It is at 1 that it stays close, right? And bounces, I mean crosses, but stays close, kind of like that. Kind of like that. Again, do we have the best picture? No, but it's correct, okay? Again, if you graph with GeoGebra, you can get the exact shape and compare it to this. Alright, so that is that number. Now let's do a few more. Let's do 48. So what are we supposed to do in 48? Here it says, write the formula for the polynomial based on what? Based on the... So for the following, use the graph to write the formula for the polynomial function of least degree. Now, what do we mean by that? So one thing that I didn't mention, I should have mentioned, is that if you have a polynomial graph, then the number of turns, so these are turning points, right? So number of turning points where the graph changes behavior actually is given by n minus 1. So an nth degree polynomial has at most n minus 1 turning points. So this has 2 turning points. So if you put 2 here and put that, right? So number of turning points, which is, this is number of turning points, has to be less than or equal to n minus 1. So number of turning points is always less than or equal to n minus 1. So nth degree polynomial can have n minus 1 turning points or fewer, right? So since we have 2 turning points, then n has to be, we can solve it here, just add 1 to both sides. N has to be greater than or equal to 3. That means the degree of this polynomial has to be at least 3, right? It could be more, but it's at least 3, based on the number of turning points. Now, we also know this has what? This has 3 roots. And so what we can do, we can write p of x equals to some a, we don't know what it is, a sub n, we just call it a because there's only one a. And then we're going to have 3 of these. What are these? Well, that's x minus the root, x minus the root, and x minus the root. But we have the roots here, negative 2, 1, and what? And 3, right? Oops. So these are the turning points. These are the roots. Okay? Now, we don't know what a is, but we could get a point on the graph, right? That point is 0, 3. What does that mean? That means when x is 0, p of x is what? Is that. So that means if I put a 3, first of all, I can simplify this, write it as a x plus 2 instead of x minus negative 2, like that. Okay, now here, if p of x is 3, then x is 0, right? So I'm just going to put 0 for x, and I'm going to put 3 for p of x, right? That's what this point is. So 3 equals to, that's 2, and that's a negative 1, and that's a negative 3. So negative 3 times negative 1 is 3, 3 times 2 is 6, so that's 6a. So from here we know a has to be 1/2. 3 over 6, which is 1/2. So that means this formula is going to be p of x equals to 1/2 x plus 2, x minus 1, and x minus 2. So that's the formula for this graph. Okay? All right. Now, let's do one more, and I'm going to do, this is going to be quickly. 58. Now 58 says, find an equation for a polynomial that is a degree 3, zeros at these, and the y-intercept is 0, 6. So basically it's exactly the same thing we just did, except the information is explicitly given. Instead of getting the information from the graph, we are actually given the information, right? So this is a third polynomial, right? So we have 3 roots, and the roots are given. What are the roots? Negative 5. Remember, the minus is part of the formula, so you have to put x minus whatever the root is, right? And then x minus negative 2, and then x minus 1, right? Those are the 3 roots. So we got p of x is a times x plus 5, x plus 2, and x minus 1. And we are given a point that when x is 0, p of x is what? Is 6. So we put 6 here, and then put 0 for x. So we got 6. Now that's 5 times 2 is 10 times negative 1 is negative 10a, right? 5 times 2 is 10, negative 10a. So a equals to 6 over negative over 10, which is negative 3 over 5, right? So that's our, and it's written here, right here. Let me fix it. So that is our formula, right? Negative 3/5 is a, and times x plus 2 times x plus 5, x minus 1. All right, so I'm going to end this video here and continue in the next video, okay? And I'm going to come back here and say bye and take care of yourself and others. And I see you in the next video. Take care.